Hey guys, Professor Amali here, and today we'll be talking about conditional probability and general rule of multiplication in probability. Okay, so we already know the general rule of addition, which is the probability of A or B of an event actually being A or B is the probability of A plus the probability of B minus the probability of A intersection B. So here, if you could try and think about this as when you have like two areas, you have area A, and then you have like area B, right? So this is B, A, and here you have like the shaded area between them. And that shaded area is your A intersection B area. Okay, so when you want to try and think about this is like the realm of the space, and when you want to try and think about well, what are the chances? Let's say some sort of variable or some sort of event could occur in A or in B, right? So again, you're trying to think about or, we would want to try and think about anything which occurs in this area. And so that's where you're trying to subtract out the common intersection because that area is being counted twice, just this blue shaded area. So when it comes to the multiplication rule, it's slightly different. This multiplication rule is the probability of A and B. That's equivalent to the probability of A multiplied by the probability of B conditional on A already occurring. Okay, so or B given A, however you call it. There's different ways you call it. And so this is the probable. This is the general multiplication rule. Okay, so in certain places this is the general rule, and when events are independent, this just becomes probability of A and probability of B. So when the two events are independent, the special rule of multiplication is just a simple straightforward. And here it is B conditional on A already occurring. Okay, so what does this conditional mean? Let's actually try and take a look at the example. Let's try and take this example over here. So a golfer has 12 golf t-shirts in his closet, and so 9 of them are white and 3 of them are blue. Okay, so he gets dressed in the dark, or grabs the t-shirt in the dark, and so he plays golf 2 days in a row. Okay, and does not do laundry yet, and wash the clean clothes and put it back into the closet right away. But it just goes into the laundry basket. So after he takes out one t-shirt, so there are 12 shirts, after he takes out one t-shirt for the first day, for the second day, there'll be only 11 t-shirts remaining. So the action of the first day affects all the actions which all the probabilities of the second day. Whereas in independent events, such as over here, this is an example of a coin toss. It's a very good example of independent events. You flip a coin once. It has no impact on whether the coin is being flipped for the second time. And you flip the coin the second time. The probability of heads still remains 50, and the probability of tails remain 50%. Okay, so these are independent events where if you want to try and think about the probability of two heads occurring or 3 heads occurring continuously, you just multiply the individual probabilities accordingly. Whereas here, if you pick out a white shirt or blue shirt, it affects the probability of picking up the white or the blue shirt in the second day. And that's why you have to try and condition the second event based on event A already occurring. Okay, so here, the probability of white and blue. Okay, so and here, what is the probability that both shirts are white? Okay, so that's what we are interested in. And so, what is the probability of on the first day that the event becomes you have a shirt which is white? Well, you have 12 shirts and you have 9 shirts which are white. So it's 9 by 12 on the first day that you get a white shirt. So assuming if you've taken and let the second event be getting a white shirt on the second day. If you've already taken one shirt off, now you have 11 shirts remaining. And out of these 11 shirts, 8 shirts are white. The probability of the second white shirt, picking up a white shirt on the second day, when the first event has already occurred, is 8 by 11. because you have 8 white shirts and 11 shirts in the closet. And so the probability that you have 2 white shirts in a row is the multiplication of those two, which is 0.55. Okay, so this can be done in the reverse. Okay, so and you could extend this multiplication rule for 3 events. For the most part, we'll be thinking about only 2 events happening here. And the more events you start going, it gets more and more complicated. And in this case, let's look at another example maybe. This is general conditional probability in a sense. Just remember, when you're trying to think about probability of A and B, it's the same as probability of A into probability of B, condition on A already happening. This is the same as you could write the same thing in the reverse order as well. Probability of B occurring and the probability that A is going to occur given that B has already occurred. These two are the same thing. Now, this is the same formula just written depending on the event. Okay, so that's the general and special rule of multiplication. And that just focus on. So the next part is contingency tables. So contingency tables are whenever it's like when you have 2 kinds of categories. It's a very nice way to try and get all these values in sort of like a nice table format. Okay, so here is an example of movies and men and women, and whether they attended 0 movies in the week or in the month, whether they watched 1 movie or 2 or more. Okay, so you had 20 men who watched no movies in the month in the survey, and 40 men watched 1 movie, and 10 watched 2 or more. Similar data is given for women, and the total number of survey respondents are given as 150 in total. Okay, so now let's say, given that we have this table, okay, so what is the probability? I'm going to make up a question, right? So what is the probability that when you select a person, you're randomly selecting a person? Okay, so what is the probability that the person will be woman and has watched 2 movies or more? Okay, so when you try and ask a question like this, so this is the probability of like male plus 2 movies. Okay, so this is the idea, and here it's given from your table. You could directly interpret this. That's 10 out of a total of 150 survey responses. Okay, so here the probability is just going to be 10 divided by 150 or 1 by 15. And so if you try and ask another question, what's the probability that there was a man and watched no movies? That will be 20 divided by 150. Okay, so what's the probability that it's just a woman? Okay, you don't care about 2 ants. And this here, you could try and think about this as, let me try and draw this table. Movie 0, 1, 2. Then women. Okay, so when you try and represent this table over here, here you have some values 20, 40, 10. This 20 can be thought of the probability of a man and 0 movies, right? And there's a probability of a man and 1 movie, probability of a man and 2 movies or more. Okay, so this number over here is the overall probability that you selected a person. This is the overall probability that you selected a woman. This is the overall probability that you selected a person who has watched no movies. No movies. Overall probability of any random person just having 1 movie. The overall probability of a person having watched 2 movies or more. Okay, so this is the overall probability, which should be equivalent to 1. Okay, so when you try and give all these things in a different kinds of table, when you try and make this a relative frequency table, so where this probability of man and 0 movies is going to be 20 divided by 150. It's going to be 40 divided by 150, and this is 10 divided by 150, and you get the idea, right? So here it'll be 40 divided by 150 again, 30 divided by 150, and 10 divided by 150. Okay, so these are the overall individual probabilities, and this probability of no movies is going to be 60 divided by 150, and so on. So you could try and find out all the individual probabilities by kind of subtracting that individual count by the total, and this would be your probability. So contingency tables can be very useful, and that's another example given in your textbook. I highly recommend you going through that. Okay, and the next part of your theory chapter is the idea of tree diagrams. The tree diagrams are another way to try and approach your probability, as you could show. This is the same example of like loyalty of this example over here. So this example over here, where you have two categories, remain or would not remain. And here you have four categories under, let's say, a young, someone who's worked less than a year, someone who's worked between 1 and 5 years, 6 and 10 years, and more than 10 years. Okay, so if the question over here is if you are given an offer, just the same offer as your present position or slightly better, just a little bit better, extra $1,000 a year or something. And would you remain within the company or take the other position? So this was your question which was asked. And now this was the table, and they did the survey for different firms, a sample of executives over here. These were the responses. Okay, so across four different categories, some of them would remain, some of them would not remain, right? So the probability of those who would remain is greater than the probability of those who would not. And all these things are given. So now what's this probability of randomly selecting an executive who's loyal to the company and has more than 10 years of service? Okay, so what will that be over here? Has more than 10 years of service, 75, and is loyal to the company. That means would remain. So that's 75 divided by 200. Okay,